My name is Hendrik-Jan Megens, and yeah, I actually shouldn't be here. Well, I should be here, but not here presenting because actually Annemiek was supposed to present her work today, but she's enjoying a nice vacation. She couldn't make it, but she wants to sort of say hi to everybody. I also would like to include Mark here. Mark has been very instrumental in all the molecular work during COVID, mostly while juggling his own PhD project, which is unrelated. So very nice that he's been able to do that. And Geert also couldn't be here today. Of course, he's been from the start instrumental to the Wageningen contribution in AQUA-FAANG. So I hope I will do justice to Annemiek's work. Let's see how that goes. So one of the things that yesterday already was quite apparent in some of the talks is that we are blessed in AQUA-FAANG to have no fewer than 3 out of 6 species that are in fact tetraploids. Tetraploids are quite interesting because what will happen to a polyploid genome over time is that the genome will try to sort of become diploid again, rediploidization, which entails gene loss. That seems quite logical. I mean, you have genes redundant, so why not? But there may be all sorts of issues with things like dosage compensation. Genes may also be retained, but then acquire specialized functions. So this is, from a genome perspective, it's quite an interesting sort of feature to study in genomes. In carp, we have a so-called allotetraploid, so that means that we actually have the product of a hybridization of 2 species. And since these genomes started out different, over time there has been no recombination. Another difference with the salmonids is that it's recent, well it's recent, 12 million years, 13 million years that this has happened, as opposed to the salmonids which like 80 or 100 million years ago when their autotetraploid event happened. So yesterday was also remarked that it's actually a very nice opportunity because you have 2 of these genomes that are traveling essentially for 12 million years in the same organism being exposed to the same conditions. So this is really very nice, so there is no recombination. At the same time, because this has been quite recent, the genomes are still quite similar, and that in itself poses problems when you have to study processes like gene loss, because if you assemble a genome, yeah, you will actually sort of compress regions that are very similar. So if like certain regions with genes are too similar, you might actually sort of assemble them into one. So how are you going to actually confirm that you have bona fide gene loss? And in addition, one of the things that you would hope to do is making full use of the fact that you have these 2 separate genomes, sort them by ancestry. And ideally, you would do that on a chromosome level. So when we started out this research, there was no genome available that was actually sort of allowing us to do exactly that. So we started out building a new genome with nanopore long reads, Illumina for polishing, and IC to make a contact map, which this is just a few years ago, actually seeing where we are currently with, you know, telomere to telomere genomes being the norm almost. It's quite mind-boggling to see how fast things are moving. But yeah, so we were actually able to create a chromosome level assembly based on high C scaffolding. This is the results. You can actually very nicely see 50 chromosomes assembled. The genome is now available through Ensemble, has been annotated by EBI. So that's a huge resource for us to use. In addition, from this contact map, maybe also referring to one of the previous speakers. One of the things that we actually don't see in this contact map is any evidence for, let's say, the Ohnologs pairs, chromosome pairs, to actually show evidence of interactions, which I think is quite interesting in itself. This is just one sample from blood, but there is really no evidence of that. So what Annemiek did subsequently is take the genome of this Poropuntius species, which is a model for one of the ancestors, and use that to sort of create a map of similarities, sort of allowing, following on the footsteps of Su et al. From 2019 to really sort of disentangle the genome into two. And so what we ended up with is this rather nice resolved sort of binning of genomes into CARP subgenome A and CARP subgenome B. Ada yesterday already mentioned this. And those chromosomes are not only syntenic to each other, but also completely syntenic to zebrafish. So the 25 zebrafish chromosomes have a duplicate representation, in a sense, in the CARP genome. So this is a very nice resource to start working on our basic problems. So then the next question is, do we actually have a complete gene set? So one of the things that you can then do is do this so-called Busco analysis, where you take a set of vertebrate genes, in this case, that we expect to be present in all vertebrates. These are genes that are selected because they have very strong one-to-one orthology in the vertebrates. And indeed, what we see is that the CARP genome seems to be, that we built, is pretty complete. What we wouldn't expect in a sort of normal diploid genome is a high degree of duplicated genes, but they're there, and of course this makes sense. But then if we look at the subgenomes, we really see that those subgenomes really each are not as complete, which certainly suggests that both of the subgenomes are necessary for a functioning organism. And in addition, subgenome A seems to be a little bit less complete compared to subgenome B, which is interesting because subgenome A overall, as Ada yesterday also already mentioned, is less expressed on average than subgenome B. So there is a hint of directional gene loss, directional towards subgenome A. So this is something that we really wanted to follow up. And this is where context really starts mattering, I think. So yesterday Ada mentioned that as you go in ontogeny, the differences in between subgenome A and B in expression diminish. They start becoming less. And so it really seems that as certain conditions change, the sort of contribution of each of the subgenome may in fact also change. So one of the things that we ask ourselves here is, what happens if you really are inducing gene expression? And in the context of our experiment, this was directed specifically at the ISGs. Thomas yesterday already mentioned a lot about ISGs. And we used the same approach, essentially, but then really selecting the most conserved ISGs that have a very high one-to-one orthology relationship within fish and even invertebrates. And so then we end up with around 100 genes of different that have different different types of genes, transcription factors, enzymes, viral sensors, but all genes induced by interferon. So in zebrafish, there's about 100 of those. And looking at CARP, Annemiek was able to actually find 91 back. And this was a painstaking analysis where she really had to sort of manually curate all these genes. because the automated annotation from Ensemble was, here was lacking here and there. This is, I think, expected. So it really requires very stringent manual curation. But after every search that you could think of, there were still 9 missing in subgenome A and 6 in subgenome B. So this really also indicates that also for this particular response, interferon-induced response, you really need to have both subgenomes. So we wanted to dissect this further and look at gene expression. And here, well, I actually will reiterate some of the aspects that were of the experiment that were already mentioned. This is actually one of the nice things, I think, within our consortium. For this particular experiment, it was done the same for all 6 species, which is actually quite special, because normally if you have live agents and you want to do an actual challenge test on live agents, yeah, that's actually very difficult to do across species because all of these viruses will be different. With this strategy, we actually have quite a uniform sort of experiment across 6 different species. So this will be recognizable. Several figures like this have been shown this morning. And what we actually turned out doing is focus on the in vitro experiment because that was giving us the clearest signal. Also talks earlier this morning already indicated that there may be some differences between what the in vivo and the in vitro experiments are telling us. So in the case of the carp, actually the in vitro was most sort of pronounced in its response and most easy to explain. Now this figure I don't expect you to study, but what I will just highlight is that we have these 100 or odd genes here that are color-coded similar to the figure earlier. And then these are the upregulations per subgenome. And what you should take home if you study this for a while is that actually there is no difference, no systematic difference between those subgenomes. So this is, in that sense, a bit of an uninformative figure because that is what the genome is telling us. Same thing if we look at the normalized counts in the controls versus the poly-IC stimulated condition, we actually see that there is upregulation, but it's not really very biased towards one of the genomes, and I can show that a little bit different in this figure, where if you look at the controls, the constituent expression is actually a little bit higher in subgenome A, which would be unexpected, but then after induction, after treatment, subgenome B is ever so slightly higher induced. But also, I mean, from a statistical perspective, not really significant. From a biological perspective, well, we can debate that. And that, of course, is something for further investigation. This is a different perspective. Looking at all upregulated genes, we actually see that there's, for each of the subgenomes, 600 odd genes that are upregulated. There is a significant overlap between the subgenomes for this experiment where genes are upregulated. But there's also a bit of a sort of a bias in one or the other subgenome. So this is all upregulated genes. Whereas if we just focus on the ISGs, we really see that those genes that we expect to be upregulated, most of them actually will, independent of the subgenome. Although there are a few genes that actually resist our expectation. And that, of course, is of some interest that we haven't actually followed up yet. So, briefly, conclusions. So we have mostly, in both of the subgenomes, we have this ISG gene set complete. And Ohnologs are both expressed from both subgenomes during an immune response. But there is not really evidence for pronounced subgenome dominance. So again, here I think this context really matters again. If you want to learn more about this, actually there's a pre-release of this paper in Genomics just out for your perusal. So if you're interested in this, I would actually invite you to look it up on the internet. And then a last word about the future. Annemiek will come back in 2 weeks' time from holidays. And there's still a lot of work to do. One of the problems that we've had with this particular experiment is that actually our chip data didn't really sort of perform to our expectations. In the end, it turned out that we chose well, in retrospect, we chose the wrong kit. What can you do? But the ATAC is currently being very actively analyzed by Annemiek. Too early yet for conclusions, but this is certainly something where we want to study further the genome architecture, the regulatory landscape, let's say, of these differences, and then see why you actually have some similarities between subgenomes, but also differences. And I think Damir yesterday already sort of highlighted some of the potential sort of differences that we might expect there. And with that, I just want to thank all our friends in the carp genetics community and the fish immunology community that have been instrumental to this work. So, yeah, thank you.